We're on page 102 of the notes in section 6.5. At the top of this page, because it's relevant, is a bit of a review for things that we have learned and maybe this past chapter or things from chapter 3. The first thing is all of the rules for dealing with exponents. If you are multiplying, dividing, raising a power to a power, raising something to 0, anything like that, that's in this first portion. And then we have the properties for logs, which we have learned in chapter 6, and all of these properties with expanding, writing as a single log, using the change of base formula, the power rule. Any of those rules that we have looked at are summarized here. And if you need to reference these, I just kept these close, and that's the whole intention behind that. We're going to be looking at solving exponential equations. And I am, let's see here, going to look at this example here where we're raising 4 to a power. And after we raise 4 to a power, the result is 20. I want you to recognize that there is 2 different approaches we could take. So we're actually going to do this twice. So here I have 4 to the power of x equals 20. And our first method for solving this is to take the log of both sides. Now, remember that when you're solving equations, the main rule is you can do what you want to do, but you have to honor the equal sign and do it to both sides. So if you take the log of both sides, so I'm just going to write log of 4 to the x equals log of 20. This would enable you to use the power rule, the x, where I can take the power and pull it out front. So I could actually write this as x times the log of 4 equals the log of 20. Now, I did this in 2 steps, but you don't have to do that in 2 steps. You could have jumped from the first step to the second. Now I can get x alone because I can divide both sides by the log of 4. Cancel it on the left. And in my calculator, I'm going to put the log of 20 divided by the log of 4. I've brought in an image of what Desmos gave me when I put log of 20 divided by the log of 4. If I was going to round this to 3 decimal places, this would be 2.161. Okay, so that was the first method. The second method is to take your exponential and rewrite it in log form. So if I have 4 raised to the power of x equals 20, and I rewrite this in log form, I would write log. My 4 would become the base, and 20 and x would change spots. If you have a calculator that can have all of these things written just the way that they are, Desmos is one of those calculators, but sometimes you don't. You would have to take this and change it to the change of base formula, which means that you would rewrite this as log of 20 over the log of 4. Notice that this is where we are over here. Log of 20 over log of 4, which we already put in our calculator, which is going to give us the same result, which is 2.161. So there's 2 different methods that you can do. And I don't think one method is better than the other. It is whatever you choose to use. Let's look at the next page. Solve the following exponential equations and round your answers to 3 decimal places. So when I'm looking at A, I just look at that and I think I am going to take the log of both sides. So if I did that, I would have 3x log of 5 equals the log of 5.6. And if I want to get x alone, I could divide both sides by 3, and I could divide both sides by the log of 5. and that would allow me to cancel the 3 and cancel the log of 5. And in my calculator, I'm going to put the log of 5.6 divided by 3 times the log of 5. And all of a sudden, magically, I have my little calculator picture up here showing my result, and that would give you 0.357 after rounding to 3 decimal places. Okay, B is a great example of looking at an exponential equation that needs to be solved that is not exactly in the proper form to start off with before I can start doing things with logs. Before I do anything where I use my tool of using logs to isolate an exponent, I need to put this in the very simplest form that is showing a power equal to something. And so what I have to do is I actually have to add 9 to both sides first. So I have my power alone, and then I can go ahead and either put it in log form or take the log of both sides. If I put this in log form, it's going to look like log base 3 of 30 equals x. And then I can go ahead and either put this in my calculator, or I can put it in change of base form, which is log of 30 over the log of 3. But I'm going to go ahead and put the log base 3 of 30 in my calculator. Magically above here, you'll see that I inserted the calculator picture. So x is going to be equal to 3.096. Pretty great. Okay, so let's look at some other examples. Here we have some exponential equations that seem like they could be a little bit more challenging, but probably very doable. If you're looking at something like this and you're like just panicking, my advice to you is to just aim for the first step. So for C, if I want to isolate my exponential, my power, I would have to divide both sides by 2. And that would give me 8 raised to the power of x minus 2 equals 12. My power has been isolated. My exponent area is a little bit confusing looking, but I'm still going to deal with this the same way I would deal with the equations we were working with before. I'm either going to take the log of both sides, or I'm going to put this in log form. If I put this in log form, it will look like log base 8 of 12 equals x minus 2. And I know that before putting anything in a calculator, I'm just going to isolate my x by adding 2 to both sides. So now I will have x is equal to log base 8 of 12 plus 2. And this is what I'm going to put in my calculator. Take a moment here. And once I put this in my calculator, my answer is going to be 3.195. It's rounded to 3 decimal spots. Go ahead and take a moment and try to do B to the best of your ability. Pause the screen and come back after you have given it a go. All right. Looking at B, this reminds me a lot of when I first started approaching being a person that does math, and I was still going to college, and given these problems that looked challenging and making the decision to take a chance and just give it a go, even if I felt like I didn't know what I was doing. Basically, I would pretend that I knew what I was doing and do the first step, and do the second step, and do the third step, and then realize by the end of all of the steps that I actually knew what I was doing all along. I just wasn't allowing myself to succumb to whatever fears I had of giving it a go and trying it out. So do what you have to do to get yourself started. What if I go ahead and take the log of both sides? So I know I've been putting things in log form over and over and over again, but this time I'm just going to take the log of both sides. Remember, if I do that, I can bring the exponential out front, exponent, which is 2x plus 3, log of 7 equals log of 81. And then I'm going to divide both sides by the log of 7. So I can cancel here. Now I have 2x plus 3 equals the log of 81 divided by the log of 7. I'm going to subtract 3 from both sides. Now I have 2x equals the log of 81 over the log of 7 minus 3. And I'm going to divide this whole thing by 2. And that's what's going in my calculator. I know it looks ugly, but this is what's going to go in my calculator. You can put this in your calculator, so I'm going to do it. And I'll bring back what it is that I got from my calculator in just a moment. Okay, so here is what I got after putting this in Desmos. My advice to you for getting things where you want them as far as this complicated quotient is strategically placed parentheses. I actually wrote all of the stuff that's inside these parentheses first. Then I put a set of parentheses around them. And then I did divided by 2, and it put everything where I wanted it to be. My answer here is negative 0.371. That is the answer to B. Let's look at the next page. We're looking now at a few different types of situations where you would need the skill of being able to solve an exponential equation, and it's looking at real life stuff. Usually the most popular exponential equations are the ones that are compounding interest. You've probably seen this formula somewhere before. All of the pieces to this really point at how much money you are starting with, the rate at which you are growing, the number of times interest is compounded in a year, and then the number of years that you have it invested. I want you to remember that the interest rate should be expressed as a decimal. It's really important. And I also want you to be aware that the number of times the interest is compounded, that is addressed twice in here. Now, I know that this is a little bit blurry, so I'm just going to write it out one more time. A equals the starting amount, principal, times 1 plus the rate over the number of compoundings raised to the power of the number of compoundings times time. So notice that this number is in here twice, and that's okay. Remember, the annual is insinuating that you're compounding once, and then you have biannual, which means twice. You have monthly. If it was monthly, that's represented by 12. Daily is represented by 365. Weekly is represented by 52, because remember, we're just counting how many weeks are in a year, days are in a year, months are in a year. So those are things, and I'm sure there's other ways to express frequency, but I think I've got most of them right there. So let's look at the first question. What interest rate, compounded monthly, do you need for $60,000 to double in 15 years? Remember that for $60,000 to double, we want to end up with $120,000. Now, if I was asking you, what are we looking for? I'm hoping that you identified that right at the beginning when it said, what interest rate? We are looking for R. So we should be able to fill out every little thing in this formula except for R. R is what we're looking for. So I'm going to go ahead. The amount A, that is 120,000, equals what we started off with, times 1 plus R over monthly, 12, raised to the power of 12 times 15. Now, there's lots of stuff I can do here. I can divide both sides by 60,000, which is going to give me 2 equals 1 plus r over 12 raised to the power of 12 times 15. 12 times 15 is 180. Now, I can't really do a whole lot unless I am able somehow to get rid of this parentheses. The only way I can get rid of this parentheses is if I were somehow able to cancel out that 180 in the exponent spot. And we can cancel it out if we multiply it by its multiplicative inverse, which is 1 over 180. And so what I'm going to do is I'm actually going to raise both sides to the power of 1 over 180. And that will allow me to cancel out my exponent. So now I have 2 raised to the power of 1 over 180 equals 1 plus r over 12. I'm just going through all of the things that I would need to do to solve for a variable. So I'm going to subtract 1 from both sides. I'm going to rewrite this up here. 2 raised to the power of 1 over 180 minus 1 equals r over 12. And if I want to get rid of 12, I have to multiply both sides by 12. And then if I put this lovely, complicated looking thing in Desmos, it's going to give me a rate in the form of a decimal. I'm assuming it's going to be like 0.0 something, but the only way to know is to put this in decimals, so let's do that. I went ahead and I placed it up here. And again, I just want to encourage you not to underestimate the power of strategically placed parentheses to make sure you're getting what you want. My rate would have to be 0.0463. So there we go. It's a 4.63% rate of interest. It's crazy, right? Seems like a lot, but it's actually doable. If you practice a few of these, you'll be really good. Many people use U.S. government savings bonds as long-term investments. When you purchase a Series 1 or EE savings bond, you pay half of the face value of the bond, and then when it matures, it has earned enough interest to be worth the entire face value of the bond. So if you invest $4,000 in Series EE bonds, how long will it take for the bonds to mature if the bond pays an average of 4% interest compounded semi-annually? Semi-annually, how many times per year is that? Well, if you don't know, you can look it up. But I'm sure if you're a person that ever shops at like Victoria's Secret or something, you would know what semi-annual means because they have those semi-annual sales. But this occurs twice a year. So semi-annual is the same thing as biannual. So that's kind of a cool thing. All right, so we have the fact that we start off with $4,000 that we invest. Now, that is the principal. Then we know that the amount we're aiming for is the full value of the bond, which is $8,000. We know that the interest rate is 4%. It has to be put in the form of a decimal. We know that the number of times compounded is 2. So there's really nothing left to look for besides the t. But you don't even need to know that because it asks you how long, and t is the only letter that represents time. So that's the thing. So we're going to use our formula. We're plugging in 8,000 for A. And I'm going to have to improve my handwriting. 8,000 for A. 4,000 for P. 1 plus 0.04 over 2 raised to the power of 2t. There it is. This is the thing. You've got lots of stuff here that can be simplified. For instance, I can divide both sides by 4,000 and cancel that out. 8,000 oops, what am I doing? It's not 8,000 no more. It's 2 now. 2 equals 1 plus 0.4 over 2 equals 2t. Guess what? 0.04 divided by 2 is 0.02. 0.02 added to 1 is 1.02. Oh, look how beautiful that is. Guess what? We have a situation where we have an exponential equation and our variable is in the exponent spot. This is just like all of the equations we had to answer and solve at the beginning of this chapter. We have to use logs. So you can do this one of two ways. I can take the log of both sides, or I can change this to log form. Does not matter. So I'm just going to take the log of both sides. Log of 2 equals, bring this down, 2 times t times the log of 1.02. And if I just divide both sides by 2 times the log of 1.02, 2 times the log of 1.02, I'm canceling my 2 and I'm canceling my log of 1.02. And if I put this in the calculator, it's going to give me the amount of time. Now, I'm asking myself, what amount of time am I going to consider reasonable? Well, the amount of time should happen within a lifetime. So, I don't know. I'm expecting this to be, if I had to guess, somewhere between 10 and 20 years. I could be wrong, but let's check it out and see. There it is. The log of 2 divided by 2 times the log of 1.02 gives me 17.5 years, which was well within my prediction, and my prediction was a shot in the dark, honestly. I only predicted that from my experiences in real life. And my experiences in real life are that I've always observed other people getting savings bonds from their grandparents, because nobody ever bought savings bonds for myself and my sisters when we were little. But it's all good. Okay, let's look at page number 4. Page number 4 addresses this whole continuous interest thing that I talked about before. When you are using natural logs and e, that in the real world, that is implying that we are talking about compounding interest continuously. So whenever you see continuously, I'm hoping that in your head you're thinking there's an e involved. This is a very simple formula. The amount equals the principal times e raised to the power of rate times time. Notice there's no n because the number of times compounded is continuously, and that is addressed with e. Okay, so they want us to double $5,000. So my p is going to be 5,000. If I double it, that's going to be 10,000. They were looking for the rate. We have time. It's 12 years. So I'm going to rewrite this with all my things. 10,000 equals 5,000 times e raised to 12 years times the rate. Now I'm going to isolate my power by dividing both sides by 5,000. So 2 equals e raised to the power of 12r, sorry. We are looking at an isolated exponential. And the only way to solve this is to bring logs in. Just remember, we're not dealing with regular logs, it's natural logs. So I can take the natural log of both sides. So I have the natural log of 2 equals 12 times r times the natural log of e. Now, I'm not sure if we've ever really talked about this much, but the natural log of e, remember that if there is not a base here, then the base is e. What did we say when you have a natural log and the base and this number equal? We say that this is equal to 1, because this is saying e raised to what power is e? That is 1. So basically, when you take the natural log of e, it's like a canceller, really, because this is equal to 1. And if that's equal to 1, all I need to do to get r alone is to divide both sides by 12. So in my calculator, I'm going to put the natural log of 2 divided by 12. If I put the natural log of 2 divided by 12 in the calculator, my rate is going to be 0.0578. There is my rate of interest for continuously compounded interest in the situation that we just had. Let's look at the last example. They want $2,000 invested. That's principal is $2,000. It pays 5%. My rate is 0.05. Interest compounded continuously means E. how long will it take for the investment to double? If the investment doubles, that means it's $4,000. We're looking for how long it takes, so we're looking for time. So if I'm using my special little handy dandy formula, my A is 4,000, my P is 2,000, my rate is 0.05, and I'm looking for time. I'm going to divide both sides by 2,000. That gives me 2 equals 2,000 E 0.05 T. I'm going to divide both sides by 2,000. Oops, nope, I can't do that. Hold on. What did I do? Go back, go back, go back, go back, go back. Oops. Okay, canceled that out. 2 equals E raised to the power 0.05 T. You know, I could stop this and go back and erase and pretend I'm a girl that never makes mistakes or overlooks anything, but that wouldn't be a thing. So I'm just going to leave that in my video and let you realize that sometimes I have to question myself and go back and fix something. Okay, so I need to solve for T. The last time we did this, we took the natural log of both sides. What if I just put this in log form this time? I have to tell you that with me, when I change something from exponential form to log form, sometimes I rewrite it first, putting my power on the left-hand side and what it's equal to on the right-hand side, which is just what I did. I just rewrote that. Now I'm going to take the natural log. My E goes down here, and my 2, and then my 0.05 T gets switched. So I have natural log base E of 2 equals 0.05 T. If I want to get T alone, I have to divide both sides by 0.05. I also want you to remember that E is here in the base spot, and that is the base either way. So I don't need to write E there. I could just write natural log of 2. But that's what's going in my calculator. Remember, if there's nothing there, we can assume it's an E. So I'm going to go ahead and take this to Desmos. And there you have it, folks. Natural log of 2 divided by 0.5 is the wrong thing. So let's go back and fix that. There, I fixed it. Natural log of 2 divided by 0.05, not 0.5. Big difference there. So if I put that in, the time that it is giving me is 13.8629. I'm going to say 13.9 years. So that is how long it would take, with interest compounded continuously, for that investment to double. Okay, I'm going to end this video and start the next one.